In this video, we will show that a limit does not exist using the two-path test. So, I've already said that we're going to show the limit doesn't exist, but in general, given a problem like this, you might not be able to tell just from looking at it. So the first thing you would want to do is see if you can use some algebra to simplify the expression first, which, if you play around with this example, you'll quickly see that there's not much you can do. So that's probably out of the question. So when that's the case, we'll usually try to prove that the limit doesn't exist. And this is the way we do it, is with a two-path test. That is, we need to find two paths of approach towards the point 0, 0, which give different limits. And the main idea is, rather to try two paths at random, the easiest thing to do first is to try all straight line paths at the same time. So, that is, we want to approach this point and take the limit as we get close to the point 0, 0. What we'll do is we'll take straight line paths that come towards the origin along straight lines. And as I said, the idea will be to do all of them at the same time. So any straight line through the origin is of the form y equals mx, where m is just some number, the slope of the line. So, if we just leave it as m, and let m be something general, we could plug in something at the end if we wanted, we'll be able to do all of these lines at once. Okay, so let's do that. Let's approach along a generic line, y equals mx. So, what we will do is we will substitute in the expression m times x everywhere we see a y. And let's simplify it and see what happens. Notice I'm writing just the limit as x goes to 0. That's because in this case, if we're approaching along a line y equals mx, if x goes to 0, then y also goes to 0. So it's sort of redundant to write that the y coordinate is going to 0. Okay, let's simplify. So we get mx to the 4th over x to the 6th plus m squared x squared. We could simplify it a little bit more. Notice that all the powers of x we see are at least 2, so we can factor in x squared out of the top and the bottom and cancel it. So on the top, we pull out an x squared. On the bottom, we pull out an x squared. And you'll see that as x goes to 0, this is equal to 0. Since the top, the numerator, if we just plug in 0, we get 0. And the bottom, if we plug in 0, we get m squared, which is not necessarily 0. So, what does this tell us? This tells us that for all possible straight line paths to the origin, the limit is equal to 0, for all of them. But we have have to be careful at this point. It's tempting to say that the limit is therefore 0, but this is not true. Recall the definition for the limit of a multivariable function. For the limit to exist, the limits must be the same along all paths of approach towards the point. And although we have tried infinitely many different paths, we have not tried all paths. We have tried only the straight line paths. In order for the limit to exist, it must be the same along all possible paths, even those that are not straight lines. So it's possible that we could take some wiggly path of approach towards the origin, and it's foreseeable that maybe we would get a different answer somehow than if we went along a straight line. So, okay, we found out that all of the straight lines give us a limit of 0, but that's actually not helpful. This tells us nothing. It tells us that maybe the limit is 0. If it exists, it has to be 0, but we still don't know if it exists. Okay. So this brings up an important point. That's a common source of confusion. This two-path test that we're doing can never tell you that the limit exists. Again, I repeat, you can never use this test to answer yes to the question, does the limit exist? The two-path test can only ever say no. It can only tell you that the limit does not exist. That's why this information we just got was kind of useless. Okay. So what do we do next? Here's where we have to get clever and try a path that's not a straight line. Well, what path? There's lots of paths that aren't straight lines. Well, let's look at the expression. The idea will be to plug in something for y that makes things cancel nicely. So notice that we have two terms in the denominator. If we cleverly choose something for y, we might be able to get those terms in the denominator to combine with each other, and then the fraction would cancel a little nicer. So, look, we have one term in the denominator, x to the 6th. That we can't change. But we have the y squared. So, we would like to pick something so that when we plug it in for y squared will combine with the x to the 6th. So let's choose y equals x cubed, because that will do exactly that. So let's approach along the path y equals x cubed. And see what happens. So then we get the limit, because x goes to 0. And again, if x goes to 0, then y goes to 0, because y is x cubed. And let's substitute. X cubed times, and y is also x cubed, x to the 6th plus y is x cubed squared. And let's simplify. X cubed times x cubed is x to the 6th, and x cubed squared is x to the 6th, so we get 2x to the 6th. And now here's where the magic happens. The x to the 6 cancels on the top and bottom. And we are just left with 1/2, and of course the limit of a constant is just that constant. So if we approach along the path y equals x cubed, which is curvy, not straight, then we don't get 0, we get 1/2. And so now we can finally answer the question. Therefore, the limit does not exist. Because we have found two different paths which give two different limits. If we approach along this curve y equals x cubed, we get 1/2. And if we approach along any straight line that we like, say y equals x, or y equals 0, or y equals 2x, any value of m that you would like, you get 0, which is not equal to 1/2. And so we can conclude by the two-path test that the limit does not exist.